Buenas tardes. Señoras y señores, bienvenidos a este Palacio del Marqués de Salamanca, donde vamos a asistir a la conferencia que cierra este gran ciclo de Astrofísica y Cosmología, la ciencia del cosmos, la ciencia en el cosmos, que con el patrocinio y organización de la Fundación BBVA, representada hoy aquí por su director, Rafael Pardo, ha sido dirigido por la doctora Ana Achúcarro, quien también nos acompaña esta tarde. Este excelente ciclo se ha extendido desde el año 2011 a lo largo de 3 cursos académicos. Han sido 18 conferencias, extraordinarias todas ellas, en las que hemos tenido ocasión de compartir la visión de autoridades mundiales sobre las materias de mayor actualidad en astrofísica. Por ejemplo, durante las últimas 5 conferencias impartidas en este curso, hemos sido partícipes de grandes avances en temas que abarcan desde la estructura de las estrellas hasta el origen de las galaxias, pasando por asuntos tan candentes como la formación y estabilidad de los sistemas planetarios o las condiciones para la emergencia de la vida en el universo. Hoy, para cerrar este gran ciclo trianual y para hacerlo con un broche verdaderamente estelar, tenemos a un conferenciante de excepción, uno de los mayores astrónomos de la época contemporánea, el astrónomo real de Gran Bretaña, Sir Martin Rees. No pudo haber habido una mejor elección para esta ocasión, pues sin duda el doctor Rees, con su profunda sabiduría, es la persona más adecuada para aportarnos una perspectiva amplia tanto del conocimiento astronómico como de los derroteros que toma la investigación actual, como de los retos que tiene planteados nuestra especie ante el futuro. Martin Rees nació en York, Inglaterra, estudió matemáticas y astronomía en el Trinity College en Cambridge y allí se doctoró bajo la dirección de Dennis Sciama. Mientras su compañero de tesis, Stephen Hawking, se dedicó prontamente a la teoría, Martin Rees se centró más en las observaciones. En palabras de Hawking, a Martin siempre le gustó estar en contacto con las cosas tangibles de la astronomía. Después de unas estancias postdoctorales en Reino Unido y en los Estados Unidos, enseñó en las universidades de Sussex y de Cambridge, y en esta última llegó a ser el director de su Instituto de Astronomía. Ingresó como miembro de la Royal Society con tan solo 37 años de edad en el año 1979. A lo largo de su carrera científica, Martin Rees se ha interesado por algunas de las cuestiones más fundamentales de la astrofísica y la cosmología. Estudió la formación de las galaxias y de los cúmulos y el origen de la radiación de fondo de microondas. Sus estudios de la distribución espacial de los cuásares llevaron a descartar completamente la teoría del estado estacionario, considerada entonces, en aquel momento, la única rival seria de la teoría del Big Bang. Fue uno de los primeros que sugirió que la fuente de energía de los cuásares debía residir en unos agujeros negros supermasivos que estarían alojados en su seno, y uno de los primeros que ofreció una explicación a la observación de las fuentes que presentan velocidades aparentemente superlumínicas. Más recientemente pasó desde la radioastronomía al otro extremo del espectro, trabajando en el origen de los destellos de rayos gamma y en el fin de la época oscura cósmica, esto es, sobre el momento en el que aparecieron las primeras estrellas. Toda esta inmensa labor se ha plasmado en más de 500 publicaciones científicas en revistas especializadas, a las que hay que añadir varios libros que han gozado de gran éxito. Martin Rees ha ocupado numerosos puestos de relevancia científica a nivel tanto nacional como internacional. Además de director del Instituto de Astronomía de Cambridge, fue rector, máster del Trinity College. Fue nombrado astrónomo real en 1995. Ha sido presidente de la Royal Astronomical Society y de la Asociación Británica para el Avance de la Ciencia. Fue presidente de la Royal Society entre 2005 y 2010. También es miembro de la Academia Nacional de Ciencias, de la Sociedad Filosófica Americana, de la Academia Americana de las Artes y de las Ciencias, etcétera, etcétera. Actualmente es miembro directivo del Institute for Advanced Study de Princeton. Su actividad, tan extensa como intensa, ha sido merecedora de numerosos premios y reconocimientos. Sus distinciones incluyen, entre muchas otras, el premio Balzan, el premio Bower del Instituto Franklin, el premio Einstein del Consejo Cultural Mundial, la Orden del Mérito del Reino Unido, la medalla Newton, el premio Peter Graeber, que es la mayor distinción a nivel mundial en cosmología, y el premio Crawford de la Real Academia Sueca, que se considera como el Nobel de la Astrofísica. Pero yo me aventuraría a pensar que quizá uno de los reconocimientos que más aprecia Martin Rees es que sus colegas astrónomos decidiesen poner su nombre a un asteroide, el asteroide 4587 Rees. A lo largo de su carrera, Martin Rees nunca ha limitado su interés a la ciencia, sino que siempre se ha interesado por los problemas y los retos sociales y por las relaciones entre ciencia, ética y política. Ha colaborado con organismos relacionados con la educación, el control de armas y la cooperación científica internacional. Fue uno de los 3 fundadores del Centro para el Estudio del Riesgo Existencial y ha sido consejero del Museo Británico, del Museo de Ciencias, del Kennedy Memorial Trust y del Instituto de Investigaciones para Políticas Públicas. En 2011 recibió el premio Templeton por una contribución excepcional que afirma la dimensión espiritual de la vida. Desde 2005 es miembro de la Cámara de los Lores, por lo que podemos referirnos a él como Barón Rees de Ludlow y naturalmente como Sir Martin Rees. Con un espíritu un tanto intrépido, se viene interesando últimamente por un tema que nos impone mucho a la mayor parte de los astrofísicos, la posibilidad de que nuestro universo forme parte de una colectividad de universos, un multiverso. Una concepción que, según sus palabras, puede ser tan revolucionaria como lo fue en su día la copernicana. Hawking, con su gran sentido mediático, ha notado que en un libro científico, cada fórmula que se incluye divide sus ventas por un factor 2, pero en cambio, que si se incluye el término Dios, las ventas se multiplican por 2. Y así hemos estado asistiendo recientemente a fenómenos mediáticos que obedecen a lemas del tipo la ciencia no necesita a Dios, el rostro de Dios, la partícula de Dios, etc. Martin Rees hace caso del primer consejo de Hawking. Trata los temas con gran claridad y sin acudir a fórmulas matemáticas en sus libros. Pero no hace caso del segundo y nunca ha seguido la tendencia de recurrir al término Dios. Muy al contrario, él se declara de acuerdo con otro colega, Joseph Silk, quien afirma que la verdadera filosofía que debe ofrecer la física moderna es la humildad frente a los grandes misterios. A pesar de todos los méritos y honores que les he mencionado, esta humildad, esta modestia, es sin duda una de las principales características de Martin Rees. Cuando un periodista le preguntó recientemente por sus ambiciones, respondió: seguir todo el tiempo que pueda con la investigación, escribiendo y haciendo campaña. Naturalmente, haciendo campaña de sus ideas humanistas. Y aunque pueda parecer paradójico, esta modestia hace aún más grande a Martin Rees. Posiblemente porque, como dijo otro parlamentario, el francés Jacques Duclos, la modestia es el único esplendor que puede añadirse a la gloria. Muchas gracias, Sir Martin Rees, querido Martin, por estar esta tarde con nosotros y bienvenido a Madrid.
Can I say it's a real pleasure to be here to give the final lecture in this series, but I should apologize right at the start that I have to speak in English. I hope the translation is adequate. Astronomy, of course, is the oldest science except for medicine. And at the risk of offending any doctors here, I'd say if it's the first science to do more good than harm. It's a fundamental science, but it's also the grandest of the environmental sciences. Indeed, the starry sky is the main feature of our environment that's been shared and wondered at by all humans in all parts of the world throughout human history. And there are 4 motives, really, which drive us to study the sky and astronomy today. And they're on this slide. We've discovered a whole menagerie of exotic objects. We've surveyed millions of galaxies. You've heard about them in earlier lectures in this series. And the volume and precision of the data we have in astronomy is unprecedented. And the scale and geometry of the observable universe is now much better pinned down, and we can trace cosmic history right back towards the first second, even the first nanosecond. We want to understand the way things are, and also how the cosmic panorama of which we're a part emerged from our universe's hot, dense beginning. And also, we want to know what the long-range future holds for us. And just a word for any students or postdocs in the audience, today is a especially good time for young researchers because the pace of advance has crescendoed rather than slackened. And instrumentation and computer power allow you to do things that we earlier generations could never do. Well, I'm going to start with a flashback to the great Isaac Newton, more than 300 years ago. He devised the first reflecting telescope, 4-inch, 10-centimeter mirror, and he must have thought about space travel. This picture from his great book, The Principia, is still the neatest way to teach the concept of orbital flight. Newton knew that for a cannonball to achieve an orbital trajectory, it had to go at a speed such that its trajectory curves downwards no more steeply than the Earth curves away underneath it. And that meant 25,000 kilometers per hour. That was far beyond what could be done by cannon of his time, and that speed wasn't achieved until 1957 with the launch of Sputnik 1 by the Soviet Union. And 4 years after that, Yuri Gagarin was the first man in space. And 8 years after that, we had this picture, iconic for environmentalists, of the sterile moonscape contrasting with the delicate biosphere of the Earth. And I cherish this picture, signed for me just a few years ago by 7 of the Apollo astronauts. Neil Armstrong didn't sign, but I did actually meet him. In fact, I gave a lecture where he was sitting in the front row, and that was a really great honor. The Apollo program was a heroic episode, but it was all over 40 years ago. If the momentum had been maintained, there would by now be footprints on Mars. But actually, people have done no more than circle the Earth in low orbit, most recently in the International Space Station. But nonetheless, space technology has burgeoned for communication, environmental monitoring, sat-nav, GPS, and so forth. We depend on it every day. And for astronomers, it's revealed the far infrared, the ultraviolet, the X-ray, and the gamma-ray sky from telescopes above the atmosphere. And unmanned probes to other planets have beamed back pictures of varied and distinctive worlds. And I'll give you a little tour through the solar system. If you're heading outwards, if you look back at the Earth from 5 million miles, you see something like this. Half Earth, half Moon, Sun coming from the right. You pass some asteroids like that, and you then get to the red planet, Mars. And here are some pictures of Mars, taken from the European Mars Express. Here's another one, a deep gorge, several kilometers deep. And in August 2012, this NASA's Curiosity probe, about the size of a car, was landed on Mars. And it's been trundling around the surface. It landed up where the little oval is in the top left of that picture, and over the next 10 years, it's going to be moving around the surface of this huge crater, eventually climbing the mountain in the center, which is several kilometers high. Here is one view which is taken, and it's already been about 30 kilometers. You can only just see it, I think. That's near the bottom of this picture, you can see little marks being made, and they are the marks made by the wheels of Curiosity, which has already been 30 miles. Well, that's Mars. Going out still further, you get to Jupiter and its 4 famous moons, first discovered, of course, by Galileo in the year 1611. And these moons are very different. Here's Io, which is sulfurous and volcanic, and here's Europa, which is covered in ice and probably an ocean underneath it. Here's the ice close up. It's probably melted and solidified many times. Out beyond Jupiter, we get to Saturn. Here's a picture where the rings are seen edge on. And this is a very nice picture of Saturn. It shows an eclipse of the sun by Saturn. It's taken by a NASA spacecraft called Cassini, which was out beyond Saturn, lined up with Saturn and the moon, and at a distance such that Saturn just blocked out the sun, but light still shines from the sun on the rings of Saturn. And just where that arrow is the Earth. You can hardly see it on this picture. Saturn has some big moons, including Titan, a moon that has an atmosphere. And Cassini carried in its cargo bay a small European probe called Huygens, which was supposed to do what's shown in this picture here. It was supposed to land on Titan, opening its parachute and do a soft landing. No one knew what it would find. And it was a great achievement in robotics because this Cassini probe launched the spacecraft Huygens 2 weeks before it landed. And for those 2 weeks, it was on its own because it takes several hours for a radio signal to get to Saturn and back. So it wasn't being controlled from the Earth. It was on its own. And it did what was expected here. And the left-hand and center picture show what it saw on the way down. The right-hand side after it landed. And this looks rather nice. You can see little lakes and rivers. But the temperature is minus 160 degrees centigrade, and those rivers are liquid methane. And those little lumps on the right are methane ice. Here's another of Saturn's moons, Enceladus, which is rather like Europa in having ice on its surface and almost certainly having an ocean underneath. Well, will people go out into space? That's a topic for another lecture. I won't say any more about that. But is life out there already? Well, there are some places in our solar system where people think there might be some kind of life on Mars, Titan, Europa, on comets, but no one expects anything very exciting in any of these places. But things are much more interesting if we widen our horizon to the realm of the stars, far beyond the distance where any probe can actually go itself. And perhaps the hottest current topic in astronomy, and there's been at least one of these lectures devoted to it, is the realization that many other stars, perhaps even most of them, are orbited by retinues of planets, like the Sun is. These planets aren't detected directly, but they're inferred by precise measurements of their parent star. There are 2 main methods, and they're both very simple, so I'll explain them both. If a star is orbited by a planet, then actually both the star and the planet move around their common center of mass, what's called the barycenter. The planet moves in a big orbit, and the star, being heavier, moves in a small orbit, like a dumbbell of very unequal masses. But the tiny periodic changes in the star's Doppler effect can be detected by a very precise spectroscopy. And here's an example where, by measuring the change in the velocity of the star towards us, you infer from this sine wave that there is a planet in a circular orbit. And you can infer from this the period of the orbit, of course, how long the planet's year is, and the mass of the planet from the amplitude of this velocity. And by this method, many groups in Europe and the US have discovered hundreds of planets. Don't worry about the details. This is just a list of planets and their orbital size. Not very up to date either. But there are many hundreds of planets found this way. But the planets found by this method are all big ones, rather like Saturn or Jupiter, the giants of our solar system. You can't find an Earth-like planet by this technique because the Earth would induce a motion of only a few centimeters per second in the Sun. And that motion, 10 to the minus 10 of the speed of light, is too small to be detected spectroscopically. But there's another technique which does allow the detection of planets no bigger than the Earth. And it's a very simple one. Supposing that you're looking at the Sun from a great distance in the plane of the orbit of the Earth, then when the Earth moved across in front of the Sun would look a bit fainter because the Earth would block out a bit of its light. About 1 part in 10,000 of the light, because the Earth's diameter is about 1% of that of the Sun. And so, if one observes the brightest of stars very accurately and looks for regular dips, that's an indication of a planet going round and round. And NASA's Kepler mission, launched in 2009, for 3.5 years, looked at an area of sky about 7 degrees across and measured the brightness of more than 100,000 stars in that part of the sky to a precision of 1 part in 100,000, and measured the brightness over and over again, once or twice per hour. And it already found more than 2,000 planets, many no bigger than the Earth. And of course, remember, it only detects planets if we're observing in the orbital plane, and for every one it finds, there must be dozens oriented differently. And this is a rather nice depiction which shows the systems inferred by Kepler, and this shows to scale the size of the planets and their orbits. Well, you may have seen in the news about a month ago that Kepler had discovered one planet that was a twin of the Earth, or a fairly close twin. And here's some information about that. The bottom half of this picture shows our solar system. The top half shows, to the same scale, a system discovered by Kepler. Kepler discovered that there are 5 planets in this system, and it measured the periods of all of them. The star, which they're orbiting, is about half the mass of the Sun and much fainter. It's a much smaller system. But the outermost of those 5 planets is about the size of the Earth, 1.2 times the Earth's radius. And more interestingly, it's in what's called a habitable zone. It's at a distance from its star such that water could exist. If it was too close in, water would boil. Too far away, it would all be frozen. So this is the best candidate for an Earth-like planet, the size of the Earth, and with a temperature where water could exist. And this is the best that Kepler's done so far. Kepler will do better, and we hope to learn more of this kind. But, of course, the real goal is to see these planets directly, not just their shadows. And that's hard. To realize how hard, suppose that an alien astronomer, this is just a movie of a simulation, suppose an alien astronomer, say 50 light years away, was looking at our solar system. Then the Sun would look an ordinary star, and the Earth would look, in Carl Sagan's nice phrase, as a pale blue dot, very close in the sky to its star, our Sun, and billions of times fainter. But supposing that the aliens had a big enough telescope that they could observe the pale blue dot, they could learn quite a bit about it, about our Earth. Because, for instance, the shade of blue would be slightly different depending on whether the landmass of Asia or the Pacific Ocean was facing them. So they could infer that there were continents and oceans, the length of the day, and something of the seasons and climate, and the vegetation, perhaps something of the atmosphere. Now, the exciting thing is that in the 2020s, say 15 years from now, we'll be making observations like that of Earth-like planets around other stars. And a especially valuable instrument in that regard will be the new telescope being planned by the European Southern Observatory. They're not very original in their names. It's called the ELT, which stands for Extremely Large Telescope. And it is extremely large. It's planned to have a mirror 39 meters across. And I would guess this room is probably about 20 meters across, so the mirror is about twice the diameter of this room. And it's not one big sheet of glass, it's about 800 bits of glass in a mosaic. And this instrument will have the combination of sharpness of resolution and sensitivity to be able to isolate the spectra of Earth-like planets around the nearest stars and draw the kind of inferences which I imagine the hypothetical aliens with their big telescope drawing about the Earth. And that will really be an exciting project. Well, what really surprised people about the planets found so far is their variety. They're not all systems like our solar system. And of course, it's very good for planetary astronomy that we don't just have one solar system. Because if you were studying animal behavior, you wouldn't just study one rat because it might have hang-ups of its own and be not typical. And we've got one solar system, and we now have others to compare it with, which aren't like it. Many have planets like Jupiter very close in. Some have planets on eccentric orbits. And there's one case at least where there are planets orbiting a double star. So on those planets, you'd have two suns in your sky. But the existence of these planets, the planetary systems, wasn't surprising. It hasn't surprised astronomers that they exist because we've had a scenario for how stars form, which is shown in this cartoon. This is an artist's impression. When a star forms, it contracts from a dusty gas cloud. Dusty gas cloud contracts under gravity, and if it's got even a slightly slow spin, it spins up faster as it contracts. And eventually, the protostar will spin off around it a dusty disk, and it's from that dusty disk that we expect planets to form. So we are not surprised that planetary systems are generic among stars. And this indicates progress. And another flashback to Newton's amusing in this context. Newton, of course, famously showed why the planets move in elliptical orbits. But he couldn't understand why they're all in the same plane, what we call the ecliptic, whereas comets are not. He thought this must be providence. Well, the argument I've just given you explains why they're all in the same plane. They all originated in a dusty disk. So that's an example of how we've pushed back the causal chain further than Newton could. And of course, the whole history of cosmology has been pushing it further back still, to the origin of stars, the origin of the atoms that made those stars, and right back to the very beginning of our universe. And this will be the theme of the rest of my talk. First, a word about stars and atoms. We see places where stars form, places like the Eagle Nebula here, 7,000 light years away. We also see stars dying. This is what the sun will look like in about 6 billion years, when it blows off its outer layers and leaves a white dwarf behind. Here's another star dying, another one dying in a rather messy way. And here's the remnants of a massive star. This is the debris from a famous supernova recorded by Chinese astronomers in the year 1054 AD. This is the record made by the Chinese court astronomer, I guess the astronomer royal of that time, who wrote that a guest star had appeared, becoming brighter than the moon and fading after a few weeks. And at that point in the sky, we now, nearly 1,000 years later, see this exploding debris. Well, it might seem far away and long ago and irrelevant, but this man here in particular, Fred Hoyle, who was my predecessor as professor at Cambridge, realized that if it wasn't for these supernovae, we wouldn't be here. He noted that a massive star, just before it dies, has a sort of onion skin structure. Stars derive their energy by nuclear fusion. They turn hydrogen to helium, helium into carbon, carbon into oxygen, and so on. And so the big star at the end of its life has a sort of onion skin structure where the hotter inner layers are processed further up the periodic table. And then, when it explodes, all that stuff is thrown out, and then it will all condense into new generations of stars. So what's going on in our galaxy is rather like depicted here. It's a sort of recycling process, an ecosystem. Pristine gas goes into stars, some of it's flung out when big stars explode into the interstellar medium, and then new stars condense from gas contaminated by the ejecta from those earlier supernovae. So, according to this story, we are literally the ashes of long-dead stars. If you're less romantic, we are the nuclear waste from the fuel that makes stars shine. And indeed, calculations suggest that each of us has inside us atoms that came from hundreds of different stars, all over the Milky Way, which each exploded 5 billion or so years ago. So we are linked to the stars more intimately than astrologers realize. We are made of material from all over the galaxy. And I showed Fred Hoyle, but the four people who really worked out this scenario were Fred Hoyle, Willie Fowler, and Geoffrey and Margaret Burbidge. And this picture was taken in Cambridge for Fowler's 60th birthday when he was given a model train, as you can see. He was a railway enthusiast. They showed that this story could explain why carbon and oxygen are common, why gold and uranium are rare, and how they came to be in our solar system. And this was a wonderful story. Well, let's now enlarge our spatial horizons from our own Milky Way galaxy, this ecosystem where gas is being recycled, to the extragalactic realm. If you could get 2 million light years away from the Earth and look back at our galaxy, it would look like this. This, of course, is the Andromeda Galaxy, our nearest big neighbor in space, 2 million light years away. It's a spinning disk viewed obliquely, where about 100 billion stars are orbiting around some central hub. Right in the middle there lurks a black hole of tens of millions of suns. And here's another well-known galaxy, a disk seen face on. And astronomers are lucky because they have a huge sample of galaxies to study. This shows a survey of thousands of galaxies in a certain sector of the sky at different distances, and what you see is that they're not distributed completely at random, they're grouped together into clusters. Now, you might think it's going to be hard to understand anything about galaxies because they orbit around each other in tens or hundreds of millions of years, so we just see a snapshot of each one because they live so much longer than astronomers, and also we can't do experiments on them, obviously. But we can now do experiments in the virtual world of our computer, the virtual universe of our computer. Just as a particle physicist can actually crash together particles, they do this at the LHC and CERN and see what happens, we can, in the virtual world of our computer, crash galaxies together. And this is what happens if two disk galaxies fall together. You have a sort of train crash, and this calculation calculates how gravity of all the stars acts on each other. And you'll end up with an amorphous elliptical galaxy. And when we look in the sky, this is a real picture of two galaxies. And having done simulations like the ones I just showed you, we can infer that these two galaxies have got dangerously close. One is raising a tidal plume on the other, and if we came back in 100 million years, they would have merged. And I should give you a warning that the Andromeda Galaxy is going to crash into our galaxy, the Milky Way, in about 4 billion years, 4 billion years. We can incidentally redo these simulations, making different assumptions about the mass of gas, the mass of stars, and putting in dark matter, etc. And it's by doing such calculations that we can come to understand quite a bit about what galaxies are made of and their evolution. The other thing we can do to test our theories is use the advantage astronomers have, which is that we can actually observe the past. We can't just infer it from fossils like geologists. We can actually observe the past by looking at distant objects. Because when we look at very distant objects, the light from them set out a long time ago. And so we can actually test our theories of galaxy formation. It's got to match the galaxy we see now. It's got to match what they were like 1 billion, 2 billion, 3 billion, 4 billion years ago, and so forth. And we can see very far back. This picture shows a tiny patch of sky, just a few arc minutes across. It would take 100 patches like this to cover the full moon in the sky. With a small telescope, this would just be a blank patch of sky. But with a big telescope, you see here hundreds of little smudges. Each of them is a galaxy, many fully the equal of our Milky Way, looking so small and faint because of the great distance, and many of them are so far away that their light set out 10 billion or more years ago, long before our solar system formed, and when these galaxies were still young. And this here is the most distant, reliably known galaxy. And just as one technical picture, let me show you here its spectrum. This is a tracing of the optical spectrum of this object. What I want to show you is that the Lyman alpha line of hydrogen, which is normally in the far ultraviolet, 1216 angstroms, is shifted to the infrared, nearly 1 micron. The wavelength is stretched by a factor of more than 8 between emission and reception. This is a very large redshift. And this allows you to infer that we're looking back when the universe was compressed by a big factor and much, much, much younger. Incidentally, this particular object was easy to get a spectrum of, despite its great distance, because what you're seeing here is not just starlight, but you're seeing glowing gas, energized not just by stars, but by a black hole in the center. And some galaxies have in their center what's called a quasar, which is a big black hole which is capturing gas and magnetic fields. So there's gas, highly magnetized gas, swirling down into the black hole, getting very hot, and that produces more power than the 100 billion stars in the galaxy. And quasars are objects where this central power source is energizing all the gas and making them brighter. So the most distant objects that we can see clearly are not normal galaxies, but they're quasars. Now, a more fundamental question. What about the early eras before galaxies formed? We have, and you've had some lectures about this, a standard time chart for the universe where we can trace cosmic history right back to a time when there were no stars, before the first billion years, and right back to the first 500,000 years when everything was hot and opaque, and right back indeed to the first second or fraction of a second. People sometimes wonder how this idea makes sense, because the standard picture is that the early universe started off almost uniform, just a hot amorphous gas. And it expanded, and it ended up in this wonderful complex cosmos that we see around us. Now, this seems somehow contrary to the famous second law of thermodynamics, the law which famously says that structure tends to wash out density contrast disappear. That doesn't seem to happen in the expanding universe. The reason for that, the answer to this seeming paradox, lies in the force of gravity. Because gravity enhances density contrasts rather than wiping them out. In a sense that any patch of the universe which started off just a little bit denser than average would feel an extra gravity, an extra slowing down, and the density contrast would grow. And it would lag behind more and more and eventually condense out. And this movie shows a segment of the universe big enough to make several hundred galaxies. The time in billions of years is on the bottom, and the expansion is subtracted out, so it looks the same size, but you see from an amorphous beginning how structures condense out. And we can compare these structures to what we actually see. And this is another picture which shows the emergence of structure in a similar volume, but in this picture we follow separately the dark matter in blue and the ordinary gas in red, which turns into stars. And by doing pictures like this, we can study how structures emerge. And we're doing this about 16 powers of 10 faster than it actually happened. Incidentally, there's one very important and gratifying point. When you do these simulations, you've got to put in some fluctuations at the beginning. If it was completely smooth to start with, it would stay smooth. And the fluctuations that are put in are not chosen randomly. They're put in from observations, because we have observations of what the early universe was like from, in particular, the Planck spacecraft, which looks over the whole sky at the background radiation left over from the Big Bang. And this radiation has a temperature which is almost uniform. It varies by 1 part in 100,000 up or down across the sky. And this picture depicts the hot and cold patches. And from this data, you can work out the fluctuations on different scales, and you feed those into your computer. And it's a great triumph that putting in what the universe was like very early on, before there were any galaxies, from this data, and running the computer forward, you end up with galaxies like the ones we now see, clustered the way they actually are clustered. That's the reason why we take this theory seriously. Here's the time chart of cosmic evolution again, from the hot, dense beginning to today's complex cosmos. And because I'm going to come back to it later, I'm going to highlight several essential requirements for the transitions from our simple hot beginning to the universe we have around us now. The first prerequisite is gravity. But gravity is actually very weak. I won't have time to go into this, but the point is that gravity is weaker than the electric and forces in an atom by about 38 powers of 10. But in any object, positive and negative electric charges cancel out. As you build up bigger objects, then say a sugar lump, an asteroid, or a planet, then gravity gets stronger because everything has the same sign as gravitational charge, but the electric forces don't mount up. So gravity eventually wins. But you've got to build up something very big before gravity wins. Indeed, if you imagine building up things, then an asteroid is not affected by gravity. A planet is made round by gravity. A planet bigger than Jupiter would be crushed by gravity, would turn into a star. But it's because gravity is so weak that stars are so big. If gravity wasn't so weak, then objects our size would get crushed. We wouldn't have such a complex, long-lived universe. So gravity is crucial, but the weaker the better. It's got to be very weak. The other thing we need in our universe is that it should depart from thermodynamic equilibrium. If our universe had always been like it was early on, then there's no complexity at all. But we live in a universe now where temperatures range from the blazing surfaces of stars to the dark night sky with the Earth in between, and that's how you can get complexity emerging. We also need to have matter-antimatter asymmetry in the Big Bang, because right back at the beginning, you have lots of particles and antiparticles, and if there were equal numbers of them, then as the universe expanded and cooled, they'd all turn into radiation. We'd have lots of radiation, but no matter. We wouldn't be here. We also need what I'd call non-trivial chemistry, tuning between the two forces important in atoms, the electric forces and the nuclear force, which holds a nucleus together despite electric repulsion. And there needs to be a fairly delicate balance in order to have the periodic table, and in order to have the possibility of nuclear fusion, in order to gain energy by turning hydrogen to helium, and so on. And we also need to have stars. We need to have more than one generation of stars, because we need the first star to make the first heavy elements, and then the second star with those heavy elements can then make planets. And we need also a tuned cosmic expansion rate, in the sense that if the universe expands too slowly and collapses very quickly, then nothing will have time to happen. Conversely, if it expands so fast that gravity is overwhelmed, then of course you get no galaxies forming. So the tuning there. And also, you need non-zero fluctuations at the beginning, because if the universe was completely smooth, then even after 10 billion years, it would still be smooth, and there'd be just cold neutral hydrogen, no stars, no galaxies, and no people. Well, going back to the time chart, we can trace things back to about 1 second. That's the time when the nuclear reactions made hydrogen and helium. Indeed, we can probably be confident back to a nanosecond. That's when each particle had about 50 GeV of energy, as much as can be achieved in the LHC, and when the entire visible universe would have been squeezed down to the size of a solar system. But questions like, where did the fluctuations come from? And why did the early universe contain the actual mix we observe of protons, photons, and dark matter? They take us back to the even briefer instance when our universe was hugely more compressed still, back before the first nanosecond was up. Eras when experiments offered no direct guide to the relevant physics. At this point, I must insert a health warning, a hazard sign, because now I'm going to talk about physics which is not battle-tested, not in the range where we can do experiments. This magazine cover, which I rather like, shows a picture of the very early universe, real size. And I show this because, according to a popular theory, the entire volume we can now see with our telescopes inflated at a temperature of about 10 to 16 GeV from microscopic size to something is the size of a tennis ball. This is an amazing theory. And there is now tantalizing evidence which is helping us to understand this very early era, an era when gravity and quantum effects meet. I showed you the fluctuations as seen by Planck. You may have read recently about a claim to have seen other kinds of fluctuations, fluctuations that aren't like sound waves, compression, but are like transverse waves, gravitational waves. And if we can detect those, that'll be another clue to what happened back early on. Back at an era where we have to worry about quantum effects, not just in the micro world as we normally do, but for the entire universe, because the entire universe was squeezed to microscopic size. So that takes us back to when things were very small. And I want to ask another question. How big is the universe? How extensive is the physical reality that's within the remit of science? Well, we can see a finite volume, a finite number of galaxies. I showed that we could see billions of galaxies. I showed you some very distant ones. But it's only a finite region, although very large. It's finite because it's a horizon, a shell around us, delineating the distance that light could have traveled since the Big Bang. But that shell around us the limit of our vision, has no more physical reality than the circle around us if we're in the middle of the ocean on a boat, which is our horizon. And just as if you're in the ocean, you don't expect that the ocean ends just beyond your horizon necessarily, then similarly, there's no reason to think that our universe ends beyond what we can see. Indeed, there's strong reasons for thinking it goes on quite a bit further. Because, for instance, if you look as far as you can in that direction and the opposite direction, conditions don't differ by more than one part in 100,000. So if the universe is some big finite structure, then because the gradient across the part we can see is so gentle, that suggests it's much bigger, probably at least 1,000 times bigger. But that's just the beginning. It could be that it goes on much, much further still, to 10 to the power 1 billion or something like that. And if it stretched far enough, then, of course, all combinatorial options will be repeated. Far beyond the horizon, we could have avatars. There could be another duplicate of this room. Indeed, maybe it's of some comfort that if you make a bad decision, you've got some avatar far beyond the horizon that's got things right. Well, be that as it may, we don't know the universe is that big. Even conservative astronomers are confident that the volume of space-time within range of our telescopes, what astronomers have traditionally called the universe, is only a tiny fraction of the aftermath of our Big Bang. As I've said, it probably goes at least 1,000 times further. And these galaxies that we can't yet observe may not be all there is. These are galaxies far away, which are beyond our horizon. And they'll never be observable because the universe is accelerating, so galaxies that can't be seen now will never be seen in the future. So even very conservative astronomers are happy with the idea that there are galaxies which we'll never ever observe, and they're part of physical reality. But there's something else. That may not be all. I've talked so far about the aftermath of our Big Bang, galaxies beyond our horizon, but the aftermath of our Big Bang. But it's possible that our Big Bang is not the only one. Indeed, there's a theory depicted here where our universe, so-called, is the bottom right, our horizon and beyond it. But that's just one domain of space-time in some possibly infinite ensemble. This is called the eternal inflation model, where we're just one island in a vast cosmic archipelago. And this is something which is the consequence of some versions of the physics for the very early universe. We don't really know whether it's correct. But incidentally, when the multiverse is mentioned, people often say, well, these domains aren't observable, so they aren't part of science. But I want to counter that by sort of aversion therapy, and that's when you start off, if you don't like spiders, having a little spider a long way away, and then you gradually end up with tarantulas crawling all over you. And so similarly, I've already said that there are galaxies which are unobservable because they're too far away, and we're used to that. So if you're used to the idea that there's a galaxy which is part of physical reality beyond our horizon, then it's not a big step beyond that to assign reality to a galaxy which is not merely beyond our horizon, but is in the aftermath of a different Big Bang. But of course, I should emphasize, we don't know if there are other Big Bangs, and we'll only take their existence seriously if we have a theory that describes physics at 10 to the 16 GeV and can be tested in other ways. In fact, a challenge for 21st century physics is, I think, to see which branch of this decision tree is correct. First, are there many Big Bangs or just one? Second, if there are many, are they all governed by the same physics or not? Many string theorists don't think that they'll have the same physics. They think that different universes will cool down governed by different physics. And if that's the case, then what we call the laws of nature, although they seem to apply even in distant galaxies we can see, may, in this even grander perspective, be just local bylaws governing our cosmic patch. I earlier went through a list of some requirements that must be fulfilled if our universe is to evolve its present complexity from simple beginnings. And it's clear that those conditions are fulfilled because of the way the physical laws are. So if there are other big bangs that give rise to universes governed by different physics, then many of them could be stillborn or sterile, because the laws prevailing in them might not allow any kind of complexity. We therefore wouldn't expect to find ourselves in a typical universe. Rather, we'd be in a typical member of the subset where an observer could evolve. And this is what's called anthropic selection. Well, I started this talk by describing newly discovered planets orbiting other stars. And I'd like to give a flashback to planetary science 400 years ago, even before Newton. At that time, Kepler thought the Earth was unique and that its orbit was related to the other planets by beautiful mathematical ratios, the platonic solids. We now realize that there's nothing in that at all. There are zillions of stars, each with planetary systems. The Earth's orbit is special only insofar as it's in the range of radii and eccentricities compatible with life, so that water can exist. And maybe we're due for an analogous conceptual shift on a far grander scale. Our Big Bang may not be unique any more than our planetary system is unique. Its parameters may be environmental accidents, like the details of the Earth's orbit. The hope for neat numerical explanations in cosmology may be as vain as Kepler's numerical quest about the planets. Well, if there is a multiverse, it'll take our Copernican demotion one stage further. Our solar system is one of billions of planetary systems in our galaxy, which is one of billions of galaxies as we can see. But this entire panorama may be a tiny part of the aftermath of our Big Bang, which itself may be one among billions. It may disappoint some physicists if some of the key numbers they're trying to explain turn out to be mere environmental contingencies. But in compensation, we'd realize that space and time were richly textured, though on scales so vast that we're not directly aware of it, any more than the plankton whose universe is a spoonful of water is aware of the world's topography and biosphere. At a conference at Stanford University a few years ago, there was a panel discussion where the panel were asked how strongly they'd bet on the multiverse concept. I said, on the scale, would you bet your goldfish, your dog, or your life, I was nearly at the dog level. Andre Linde, who had spent 25 years of his life developing the inflationary universe, he said he was far more confident. He devoted 25 years to the inflationary universe and eternal inflation. And the great theorist Steven Weinberg then said he'd happily bet Martin Rees's dog and Andre Linde's life. Now, just a brief word about the far future. Long-range forecasts are never reliable, but if we look ahead to the far future, the best and most conservative bet is that we have almost an eternity ahead, an ever colder and ever emptier universe. Galaxies accelerate away and disappear over an event horizon, like things falling into a black hole. All that's left will be the remnants of our galaxy and Andromeda and its smaller neighbors, which will have crashed together, as I showed you. Protons may decay, dark matter particles annihilate, occasional flashes when black holes evaporate, and then silence. That's not quite my final word. If one wanted a logo for this research area, I'd choose this, an Ouroboros. This image depicts the interconnectedness of the microworld on the left and the cosmos on the right, the inner space of atoms and the outer space of the universe. Now, there are links between small and large, left and right. Our everyday world of life and mountains is determined by atoms and chemistry. Halfway up, there's a left-right link between the nuclei within atoms and stars, which are powered by nuclear physics. And higher up, there's another link. Galaxies are seemingly held together by swarms of subnuclear particles that make up the dark matter. The left-hand side is the domain of the quantum. On the right-hand side, Einstein's gravity theory holds sway. Now, General relativity and quantum theory are the twin pillars of 20th century physics, but they haven't yet been meshed together into a single unified theory. In most contexts, this doesn't impede us, because their domains of relevance don't overlap. Astronomers can ignore quantum fuzziness when calculating the motions of planets and stars, because they're so big on the right-hand side. Conversely, chemists can safely ignore gravitational forces between individual atoms in a molecule because they're nearly 40 powers of 10 weaker than electric forces. But at the very beginning, everything was squeezed so small that quantum fluctuations could shake the entire universe. So there are two frontiers of physics, the very small and the very large, and we need the synthesis symbolized at the top, gastronomically as it were, to understand the very early Big Bang. But before leaving this picture, I want to emphasize that there's a third frontier, the very complex. Insects, people, and mountains. And we ourselves, the most complicated things we know about, are midway between atoms and stars. Very large compared to atoms, so we could have layer upon layer of structure, but not so large that we're crossed by gravity like a star is. Indeed, the geometric mean of the mass of a proton and the mass of the sun is about 50 kilograms, within a factor of 2 of the mass of each person here. And the third frontier, the frontier of complexity, is the most challenging one. Even an insect, with layer upon layer of complexity, is harder to understand than a star, where intense heat and compression by gravity precludes complex chemistry. And this is the famous flea drawn by Newton's least favorite colleague, Robert Hooke, a pioneer inventor of the microscope and a wonderful draftsman. Well, I mentioned this, that the challenge is complexity as well as the very large and very small, as a digression to highlight the unity of science, plus a gesture of, as it were, deferential modesty to the 99% of scientists who are neither particle physicists nor cosmologists, because they're challenged by complexity, especially in living systems. Well, we made extraordinary progress. 50 years ago, cosmologists didn't know there was a Big Bang at all. Now we can draw quite precise inferences back to a nanosecond. So in 50 years, debates that now seem flaky speculation may have been firmed up, including whether there's a multiverse or not. But, and I'm perhaps sticking my neck out here, I think we should recognize that at some stage we might hit the buffers because our brains don't have enough conceptual grasp. Our minds evolved to cope with life on the African savannah, where our remote ancestors live, and they haven't changed much since. And it's surprising we've got so far in comprehending the counterintuitive microworld of atoms and the vastness of the cosmos. But just as a monkey can't grasp quantum theory, there could be aspects of reality whose elucidation must await some post-human, superhuman intellect. Maybe these intellects are out there already in space, but if not, they might emerge in the far future. Finally, I want to draw back from the cosmos, or from what may be a vast array of cosmoses, and focus back closer to the here and now. I'm often asked, is there a special perspective that astronomers can offer to science and philosophy? Well, we view our home planet in a vast cosmic context, and we'll discover whether there's life out there. But I think the most significant thing astronomers can offer is an awareness of an immense future. The stupendous time spans of the evolutionary past are now part of common culture, unless you live in Kansas or parts of the Muslim world, perhaps. We know our present biosphere is the outcome of more than 4 billion years of Darwinian evolution. But, and this is my point, people still somehow think that we humans are necessarily the culmination of the evolutionary tree. And that hardly seems credible to an astronomer. As this time-lapse illustrates, our sun formed 4.5 billion years ago, but it's got 6 billion years more before the fuel runs out, and it flares up, engulfing the inner planets. And the expanding universe will continue for much longer, perhaps forever, becoming ever colder, ever emptier. I'd like to quote Woody Allen, eternity is very long, especially towards the end. So any creatures witnessing the sun's demise 6 billion years from now, they won't be human. They'll be as different from us as we are from a bug. Post-human evolution, here on Earth and far beyond, could be as prolonged as the Darwinian evolution that's led to us. And Darwin himself realized that no species now existing would survive. But indeed, we would strengthen this conclusion now, because future evolution won't happen on the Darwinian timescale. That's stopped for humans anyway. It'll happen on the technological timescale, where we can let machines take over or use genetic modification. So we don't know whether the long-term future lies with organic or silicon-based life. But my final thought is that even in this concertina timeline, extending billions of years into the future as well as into the past, this century may be a defining moment. Because over most of history, threats to humanity have come from nature: disease, earthquakes, floods, and so forth. But this century is special. It is first when one species, ours, has Earth's future in its hands and could jeopardize not just ourselves, but life's immense potential here on Earth and far beyond. We've entered a geological era called the Anthropocene. So this pale blue dot in the cosmos is a special place. It may be a unique place. We're its stewards at an especially crucial time. And that's a message for all of us, whether we're astronomers or not. Thank you very much.